Hello. In this video, we are continuing to characterize matter and build up our list of physical variables, or what we call state variables. We can fully describe the state of matter using these state variables, reproducing that same state somewhere else on the planet, like France. Our list of physical properties or state variables is growing. In previous lectures, we have described volume, mass, density, and moles of matter. In this lecture, we will add one more critical measurement to this list: pressure, something we all experience. Pressure is a critical measurement in chemistry. There are two ways that we can look at pressure. The first one is pictured in the slide. What we see is a piston with a given surface area sitting on a piece of matter with weights of known mass applying a force down upon the matter. The force down is easy to calculate. It's our old friend, the weight measurement, where the weight is equal to the product of the masses on the piston times gravity, F equals ma, where A is the gravity constant. Again, if all the measurements are in SI units, we will get a value with the derived unit of newtons. Now, if we apply the weight on a really big piston, the pressure that the matter feels will be substantially less than if we apply the same force on a very small piston. Pressure is inversely dependent on the surface area, but directly dependent on the force. Notice how this is represented in the slide. So, we define pressure as being the force applied per unit area. The units in SI will be newtons per meter squared, which equals kilograms per second squared meters. This final derived unit is called a Pascal, named after the great French mathematician, physicist, and inventor Blaise Pascal. The microscopic interpretation of pressure is that it's the sum of the force of all the collisions of particles with the surface of a given area. The second way to think about pressure is using an instrument invented by the great Italian physicist and mathematician Evangelista Torricelli called a barometer. He took a tube filled with mercury, Hg, and inverted it into an empty pan. The mercury drained out of the tube, but not all of it. Eventually it stopped at a certain height above the surface of the liquid in the pan. What has happened is that the force of the weight of the liquid in the tube is equal to the force of the air pushing down on the mercury in the pan, and opposite of the liquid in the tube. The pressure of the liquid in the tube pushing down is equal to the pressure of the air pushing it up. We measure the pressure by a simple formula. Pressure equals the density of the liquid times gravity times the height of the liquid, or pressure equals rho gh. On a normal day at sea level, this height is about 760 millimeters of mercury, which is also known as 760 torr, where a torr of pressure is named after Torricelli, the inventor. Looking at our density table from the earlier lecture, we find that liquid mercury has a density of 13.595 grams per mil, almost 14 times denser than water. Of course, we have already used the gravity constant, G equals 9.80665 meters per second squared. Now we want everything in SI units, so we need to convert the height of the mercury to meters and the density to kilograms per meter cubed. Plugging it all in, we get a value of 1.01325 times 10 to the fifth kilograms per second meter, or pascals. This amount of pressure can be expressed in other units too. A normal day at sea level is said to have a pressure of 1 atmosphere, and in U.S. customary units is 14.696 pounds per inches squared, or PSI for short, where the pounds value is not a mass but a weight, force, over area, inches squared. You can see by looking carefully at the magnitude of the numbers that a Pascal must be a very fine and small pressure unit. One other unit we use for pressure is called a bar, which is equivalent to 1.00 times 10 to the fifth pascals exactly. All of the different pressure unit relationships can be seen on this slide, and you need to be familiar with them. As we observed earlier, the pressure of the mercury in the barometer tube is said to be equal to the pressure of the air on the barometer pan. The barometer then turned out to be a big hit for predicting the weather. If the mercury in the tube is falling, the pressure of the atmospheric air must be falling, and this implies that a low pressure front could be moving into the area and storms might be ahead. If the pressure is rising and the mercury in the tube is going up, high pressure air must be moving into the area and clear skies could be ahead of us. Hey, that looks like good weather for some golf. The mercury barometer and manometer is still a viable way to measure pressure. That being said, because of mercury's toxicity, the trend is to minimize the use of mercury in chemical benchtop measurements. So we will find mostly mechanical and digital pressure gauges in use in laboratories these days. So pressure is now added to the list of state variables we use to characterize a system. In another lecture, we will describe a measurement we all know and love: temperature, which is the quantity we will rely on to measure energy content in a piece of matter. So I'll see you in the next video.